Hello students. So this is going to be the second lecture on electrochemistry. In previous class we have seen the basic formalisms in electrochemistry, like what is reduction, oxidation, what is an anode, what is a cathode, and then we studied in detail the processes involved in a Daniell cell. Daniell cell means one in which we have zinc and copper as electrodes. And then we have especially stressed on the importance on salt bridge. Also, we introduced the concept of electrode potentials. We have studied what is reduction potential, what is an oxidation potential, and how can we find the total potential of any cell given that you know the reduction potentials of anode as well as cathode. So I'll just write that equation once again. So we know that in general, E0 of any cell will be equal to E0 of cathode minus E0 of anode. So now we are going to do some problems based on this equation. So you can note on the problem. Given the electrode potential of magnesium equals minus 2.36 volt and the electrode potential of aluminium minus 1.66 volt, which is better anode. So if you look into the basics, we know that anode always does oxidation, right? So anode always does oxidation, and we have given, the question is given two electrode potentials, one of magnesium and another of aluminium, and we need to check whether the given potential is actually reduction or oxidation potential. So if you see in this case, magnesium is being reduced from +2 oxidation state to 0 oxidation state, which means this is obviously a reduction potential. What is in case of aluminium? There the oxidation state is changing from +3 to 0. So same way this is also reduction. Hence the given value is a reduction potential of aluminium. So both given is reduction potential. We need to find which among this will be a better anode. Since anode has oxidation taking place at that range, we need to find which among this has higher oxidation potential. But we also knows that oxidation potential is equal to negative of reduction potential, right? Negative of reduction potential. So higher oxidation potential means lower reduction potential by considering the value of negative. Okay. So if higher oxidation potential means lower reduction potential, and this will constitute a better anode. This will gives better anode. So since we have got the reduction potential of both magnesium and aluminium, now we can just choose which is the smaller value among this. By considering the convention of negative sign, we know that the one with higher magnitude carrying a negative charge will be smaller value than a smaller value carrying a negative charge. Okay, so that's a basic thing. We know that -3 is obviously smaller than -2. So we are using the same convention here, which means here we are going to consider minus 2.36 volt as a smaller value than minus 1.66, which means considering the reduction potential, which is smaller, obviously this is a smaller reduction potential value. Therefore, that is going to be the higher oxidation potential value, and hence magnesium is going to be the better anode. Okay, since magnesium has lower reduction potential, which means their oxidation potential will be higher. Therefore, magnesium is going to have or behave as better anode. If this is going to confuse you, there is another way to do this. What you have to do is, since you want anode, which is oxidation, and what you have got is both reduction potentials, just convert both of them into their oxidation potentials. How would you do that? Since reduction potential is given, now you need to convert into oxidation potential, which means EMG to EMG2+. And this will be just the opposite of reduction potential, which means just change minus to plus. This will be plus, the magnitude is same, 2.36 volt. And in case of aluminium, Al to Al3 plus, that is oxidation, is plus the same magnitude, 1.66 volt. So we need higher oxidation potential. Therefore, the one with higher oxidation potential is this. Again, magnesium is the better anode. So for this question, the answer is magnesium. Now, suppose in the question, they have just given you the electrode potential of magnesium is. They haven't mentioned whether it is reduction or oxidation. In this case, it is clearly evident that it is reduction, but in some question, they may not specify that. So in general, potential, if they have mentioned only potential, they did not say whether it is oxidation or reduction. In general, potential means what? They always mean reduction potential. Okay. So we usually say values for reduction potential and then take the negative for negative or the opposite one for oxidation potential. So if in the question it is not mentioned whether it is oxidation or reduction, please consider that one as a reduction potential. Hope that's clear. Now let's do a similar question. Question number 2. Consider a cell with zinc as cathode and copper as anode. What is the electrode potential of that particular cell? So we have given the reduction potential of copper, which is plus 0.34 volt, and the reduction potential of zinc, which is minus 0.76 volt. So if you're very familiar with the concepts, by reading the question itself, you might find there is some abnormality here, because we know that zinc is more electropositive than copper. So just because of that, zinc always prefers to be in the anode and copper prefers to be in the cathode, because anode should undergo oxidation and zinc has more ability to self-oxidize. But the question, if you see, zinc is given as cathode and copper is given as anode. And now we have to find what is E0 cell. Anyway, let's try to find it out. You know, E0 of cell is E cathode, E0 of cathode minus E0 of anode, given that both are reduction potential. Okay, so what is E0 of cathode? Cathode here is zinc and the reduction potential of cathode is minus 0.76 volt. Minus, what is E0 of anode? Anode is copper, so E0 of anode, which is reduction potential of anode, is 0.34 volt. 0.34 volts. 34 volt. So what is the final answer? When you add this up, you will actually get minus 1.1 volt. You know that in general for Daniell cell, the electrode potential of the, not electrode potential, the potential of the cell, E cell, was actually 1.1 volt. Now if you reverse the anode and cathode, what you're going to get is a same magnitude with a minus 1.1 volt. So is there anything wrong with this? So in general, by convention, E0 of cell should always be positive. Okay. For what? For a cell to be feasible, or for a cell to be feasible. This means that the reaction will be spontaneous. So for spontaneous reactions, E cell should be a positive value. Okay. So which means that if E cell is a negative value, then that cell is not feasible. So in this question, as you can see, since we have a negative cell potential, which means this is not a feasible cell. Not a feasible cell. So any cell which has zinc as the cathode and copper as the anode will not be feasible. Just see how you have seen that this is for a spontaneous reaction. What is the actual criterion for spontaneity that we have studied in thermodynamics? It was based on delta G, right? So actually we have studied that actual criterion for spontaneity is that delta G has to be negative for spontaneous reaction. If delta G is positive, delta G is equal to positive for a non-spontaneous reaction. And what if delta G is equal to 0? Then it is going to be in equilibrium. If delta G is negative for a spontaneous reaction, just now we have seen that E0 cell should be positive for a spontaneous reaction. Now, how do we relate delta G and E0 cell? There is a very famous equation for that, and this is how we represent it. Delta G is equal to minus NF cell. Let's see what are the terms involved. Delta G is equal to minus NF cell. So delta G is obviously change in Gibbs free energy. N represents the number of moles and F represents Faraday. Faraday is actually a constant value which is equal to 96500 coulombs. This is a constant value and that is called as 1 Faraday. So 1 Faraday is equal to 96500 coulombs. And finally E cell is the cell potential. So this is the equation connecting change in Gibbs free energy during any reaction and the cell potential of that particular reaction or that particular cell. Now if we say that if delta G is negative, that means if the reaction is spontaneous, delta G has to be negative. If that is negative, what happens? Here again we have a negative. So both of these will get cancelled. And then we will have the number of moles, which is obviously a positive value, and then Faraday, which is a constant and a positive value. And finally what is left out is E cell. If delta G is negative and both of these cancel out, then we should have a positive value pending, right? So positive value pending means E0 cell or E cell has definitely be positive. So this definitely has to be positive. What if it is negative? You will get delta G. What if it is negative means if you try, there is already a negative sign. N is positive, F is positive, and E cell is negative. So both these negatives will cut and give you positive value, which in turn will mean that your delta G will be a positive value. And if your E cell is negative, delta G will be positive and the reaction will not be spontaneous. It will be non-spontaneous and the cell will not be feasible, just as in case of this particular cell. Okay, so for any cell to be feasible and the reaction to be spontaneous, delta G should be negative and E0 cell should be positive. And one more thing to be noted, this is number of moles of what? This is number of moles of electrons. Or more accurately, you can write it as the number of electrons involved. That is the perfect way to write. Number of electrons involved. Okay. So when we usually study a system, we get a combination of anode and cathode, right? And then we find what we usually find from the equations is E0 of the cell as a whole, and to find this we use the cell potential, the electrode potential of cathode and also the electrode potential of anode, and by using both you find the cell potential of the entire cell. In that case, each of these we can call it as half cells. This is a half cell and this is also a half cell. And we find the potential for the entire cell. Now what if I want to find the potential of only one cell? That means I want to find the potential of a half cell. If suppose I want to find the potential of this anode, how is that possible? That is only possible if I know the overall cell potential as well as the potential of cathode. So this should be known, and the overall cell potential, both should be known. And from the same equation I can find what is the potential of this particular half cell, that is the anode. And also the same procedure can be used to find what is the what is the potential of cathode also. That means the half cell potential. So any half cell whose potential is already known means called as the standard or the reference cell or reference electrode. And the usually which we use is hydrogen. So you might have heard about SHE, She electrode, which actually shows standard hydrogen electrode. So the electrode which has the known potential or which we usually use as a reference is hydrogen electrode in standard conditions. Therefore, we call it as standard hydrogen electrode. Now, this electrode actually has a potential of around 4.44 volt. This is the actual potential. But hence, we have to use it for some comparison purpose. We have referenced this into 0 volt. This is the referenced potential. This is simply for the ease of calculations. We have referenced hydrogen electrode as 0 volt. So if in previous class we have actually given you the electrochemical series, there if you go and see, you will find that hydrogen has a reduction potential of 0 volt. That is the reference reduction potential of hydrogen. So now let's see what is the constituents of a standard hydrogen electrode. So in this particular system, we will have the electrolyte solution which will be composed of HCl. And since it is in standard conditions, this has to be 1 molar concentration and at 25 degrees Celsius or 298 Kelvin. This electrolyte solution should be in standard conditions, and the one which we use is hydrochloric acid solution. And secondly, we will have an electrode. Since it is called hydrogen electrode, we should be using hydrogen. But we know it is practically impossible to get hydrogen in solid form. So we use it in gaseous form itself. But for that we use platinum wire as a medium. This platinum wire, or more accurately, this is PPP. Let's see what's PPP. This actually refers to platinized platinum plate. Platinized platinum plate means it's simply a platinum plate which is coated with platinum black, or simply you can say it's a platinum wire. And this is a medium for hydrogen gas to act as an electrode. So as you can see in the setup, we have an electrolyte and platinum wire. So where do we send the hydrogen gas from? As you can see, there is an opening right here. There is an opening. So this is where you will be sending the hydrogen gas. And again, this also has to be in standard conditions. So that will be 1 atm pressure. So concentration of gas is always mentioned in terms of pressure, and the temperature will also always be maintained at 298 Kelvin, and the pressure will be 1 atm. For gas, we concentrate on the pressure, and for the electrolyte solution, you will be focusing on the concentration. So on entirety, this will be in standard condition. The standard hydrogen electrode can be used both as the cathode as well as the anode. And we know that anode is always represented on the left and cathode on the right. So when you consider this case, you can see if this is the standard hydrogen electrode, it is on the right side. So this is a scenario in which your standard hydrogen electrode is acting as a cathode. And this is the second case where again this SHE is on the left side. When you consider only these both, you can see SH is on the left side, which means this is a scenario where she acts as anode. So when it acts as anode, it will get oxidized. When it acts as cathode, it will get reduced. So it's obvious that when will they act as both of these, right? if the electrode potential, that is the reduction potential of the complementary half cell, is greater than that of the hydrogen electrode. That means if the reduction potential is a positive value for the other half cell, then in that cases she will be anode. If the reduction potential is negative for the other half cell, in that cases she will act as cathode. Okay. So for example, if we take a combination of zinc and hydrogen, or zinc and the She electrode. In this case we know zinc has what? Zinc will have a negative reduction potential, and obviously she has zero reduction potential. Which is greater? She has a greater reduction potential, therefore in this scenario she will act as cathode. The one with higher reduction potential is always the cathode. But if we consider a combination of copper and She, in that case we know that copper has a positive reduction potential and She has 0. In this scenario she will act as anode. Okay. Now let's do a slightly more difficult question based on the oxidation and reduction potential of anode and cathode. The question: the reduction potentials of 3 electrodes, that is A, B and C, are given, or more accurately if you check, what is given is the oxidation potential. A converting to A plus, B converting to B plus and C converting to C plus, which means that here we have got the oxidation potential of 3 different electrodes. So the question part A is, create a cell with maximum efficiency. So you know that if you want to create a cell with maximum efficiency, the reduction potential of its cathode should be very high and the oxidation potential of its anode should also be very high. So since only oxidation potential is given here, for our ease it's always better to write reduction potentials also. What will be reduction potential? Just the opposite of this. This is minus 0.3, so this will be plus 0.3 volts. Similarly, this is minus 0.5, so this has to be plus 0.5 volts. In case of C, plus 0.7 volt, it will have a reduction potential of minus 0.7 volt. Now we have to create a cell with maximum efficiency. And as I told, for part A, we require a cell with anode having maximum oxidation potential and cathode with maximum reduction potential. So now let's check into the data which has the maximum oxidation potential. Looking in the oxidation potential value, we will see that the maximum value is for C, that is 0.7 volt. That is the maximum possible oxidation potential among the 3 electrodes. Now which has the maximum reduction potential? We have plus 0.3, plus 0.5 and minus 0.7. So obviously the highest value is plus 0.5 volt. So a cell which will have electrode C as its anode and electrode B as its cathode will be the cell with maximum efficiency. Okay, so which means here we have to choose the anode as, which was the anode, that is C, electrode C, and the cathode as electrode B. Okay, so let's check its efficiency also. How do we check? That is E0 of this cell, which is made up of C and B, should be equal to E0 cathode minus E0 anode. Remember, both should be reduction potentials. What is the reduction potential of the cathode, that is B? It is 0.5 plus 0.5 plus 0.5 minus, what is the reduction potential of anode? That means this value. The reduction potential of anode is minus 0.7. That means minus of minus 0.7 volt. That will be plus 0.5 plus 0.7, and the answer will be 1.2 plus 1.2 volt, okay, which is fairly good cell potential. Okay, So next question, or the second part of the question, consider the cell with A as cathode and B as anode. Compare the efficiency of cell with a cell constructed from part A, which means we are supposed to find the cell potential of a cell which is created from A and B and compare it with already constructed one. That means the cell which we chose here, which has a potential of 1.2 volt. Now for that again we need the reduction potentials of A and B. So let's write that again. E0 of cell will be E cathode minus E anode. So here cathode is what? A is cathode. What is the reduction potential of A? Plus 0.3 volt. So plus 0.3 volt minus reduction potential of anode. Anode is B here, and reduction potential of B is plus 0.5 volt minus plus 0.5. If you do this, the answer will be minus 0.2 volt. So from this it's clearly evident that a cell which will have A as cathode and B as anode is obviously a non-feasible cell. The cell is not feasible. And if they have asked to compare it with the cell constructed from part A, which is a cell with a high or a very good cell potential value, so on comparing we get that obviously the part A cell is a much more feasible cell than part B, or exclusively you can say cell constructed from part A is a feasible cell and that of part B is a non-feasible cell. Now the C part of the question, check the feasibility of the cell with B being cathode and C being anode. So you don't have to even try it, because if you have a cell with C as anode and B as cathode as a feasible one, then if you reverse them, okay, here it is not being even reversed. So you look properly, B is being cathode and C is being anode. That means it is just this combination. Okay, check the feasibility. So we have already checked it in part A itself and found that it is a feasible cell. So for C, the answer is yes, it is a feasible cell. That is from part A. So that is about this question, and it's always important that, or it will be easy for you if you write the oxidation potential and the reduction potential of the given electrodes separately. It will be very easy and convenient for your calculations. Now we know that we have seen the relation between delta G and E, right? The relation was delta G is equal to minus NF E cell. And one thing we know about delta G is, or G in general, is that it is actually an extensive property. And extensive means they depend on the amount of substance present. So what about E? Is E extensive or intensive? That means E cell is extensive or intensive. How do you find it out? Let's write E in terms of G. This is delta G in terms of E. Now if you write E in terms of delta G, you will have E cell is equal to minus delta G divided by NF. Okay. Now if you see, E is actually equal to what? Delta G by N into 1 by F, right? If I just want to separate this part out, I can write E cell is equal to minus delta G by N into 1 by F. What is the purpose of that? I have told you just now that delta G is an extensive property. This is known to us from thermodynamics. But even though delta G is extensive, delta G per mole, that is delta G by N, is actually an intensive property. Why? Because no matter how much the amount of substance change, this quantity is always for 1 mole and that will be a constant. So it is an intensive property, means it is independent on the amount of substance. Here you can see that E cell is being equated to this value, that is delta G by N, which is an intensive value, and then it is multiplied by a constant. You know F is a constant, so 1 by F is also a constant, and this is equal to minus delta G by N into 1 by F. So an intensive property into a constant. So E cell is also an intensive property. Therefore, you have to write E cell or A0 cell is an intensive property. Special about an intensive property, intensive properties can never be added. Okay, while extensive properties can be summed up or they can be added, intensive property cannot be added. We can say that they are additive. They can be added as well as subtracted, while intensive properties are not. Or you can say they are not additive. Okay. Now, what is the relevance of these two things that I've learned just now? For that, we have to do one more question. So, this is the fourth question. So, the question is, given that I2 plus 2 electron gives 2 I minus, the electropotential value is given. Br2 accepts 2 electrons giving 2 Br minus. For that also the potential is given. So since the mentioned reactions here are accepting of electrons, it means both of them are reduction reactions. So the cell potential or the electrode potential given will be reduction potentials. Both of these are reduction potentials. Now the question is, which among the following statement is true? So there are four options given in which different species are reducing certain other species. We need to find which of them is correct. So to answer this question, we initially need to write the equation of this cell or the cell reaction completely. What now we have among these two is just the reactions of the reduction of I minus or reduction into I minus and Br minus. So using this, that means using an iodine electrode and a bromine electrode, we are supposed to construct a cell. So while constructing a cell, we are the ones who should choose which should be anode and which should be cathode. And how do we choose it? By understanding which will be having the higher reduction potential and which will be having higher oxidation potential. So on looking at this, we are given two reduction potential values. The higher one is obviously for bromine, since it is 1.69 greater than 0.54. So the higher reduction potential value is for bromine. So bromine will act as cathode and iodine will be anode. Okay, so cathode should undergo reduction. Therefore, the reaction of bromine should be as given. That means the reaction of bromine should be just as it is given. Let's see what that will be. It has to be Br2 accepting 2 electrons to become 2 Br minus. Now this is the cathode, so there should be a reduction reaction. But iodine should act as anode, so the reaction should be oxidation. Here it is given as a reduction reaction. So to write the cell reaction, we should just reverse this. When you reverse the given reaction, you will get the oxidation reaction. So oxidation means reversing this. So you will have 2I minus giving 2 electrons plus I2. Okay, how do we say it is oxidation? Because in case of bromine, it is actually going from 0 to -1 oxidation state. It is a reduction reaction. For iodine, it is going from -1 to 0 oxidation state. So it is an oxidizing reaction. And also, this is reduction, this is oxidation, this is acting as cathode, iodine acting as anode, and we also need to write the cell potential values, right? So the E0 for this will be just as what is given. It is 1.69 volt. But E0 for iodine or for this particular reaction, the E0 will be, since we have reversed the reaction, we have to reverse the value of E0. Just put a negative sign, minus 0.54 volt. That is the electrode potential for this particular reaction. Now we can write the overall reaction for the cell. Okay, so if you sum the reactions for the electrodes, you will get the reaction for the cell or the cell reaction. So two electrons, they can be cut. So what is left? We have Br2 plus 2I minus, giving 2Br minus plus I2. This is the overall cell reaction. Now from this, can we choose the answer, correct option? So options are I minus reduces Br2, Br minus reduces I2. So but one thing we know clearly from the question is, who is the one which is being reduced? Cathode is the one that will undergo reduction, which means bromine is being reduced here. So we have to note that we'll say bromine in general is being reduced, not iodine. Iodine is oxidized, is being reduced. So you can say iodine, we don't know which species of iodine, but iodine is being oxidized. This is one thing we can understand from the two reactions that we have. Okay, so from this we can actually eliminate out two options. Because bromine is being reduced, there are two options which says iodine is reduced. See, in this option B, they are saying bromine is reducing iodine. In option D also, they are saying the same thing. So both of these are actually wrong. We can eliminate them just as it is. Now the confusion is between whether I minus is reducing Br2 or I2 is reducing Br2. For that, let's simply check the overall cell reaction. Here you can see Br2 is being treated with what? I minus. And because of their reaction, Br2 is becoming Br minus and I minus is becoming I2. What does this mean? That Br2 is reduced to Br minus because of I minus. That means I minus is reducing Br2. Here I minus is reducing Br2 and not I2. I2 is in the product side. So what is the correct answer? It's clearly understood from the cell reaction that I minus is reducing Br2. So the correct option is A. Hope that's clear. Now, just as I told, the relevance of E being an intensive property can be understood from this. That means here I have I2 plus 2 electrons giving 2I minus. Let's suppose we take that equation. I2 plus 2 electrons giving 2I minus. And what is the cell potential? The electrode potential? It will be 0.54 volt. Okay. Now, if I just simply multiply throughout the reaction with a 2, that means I'm increasing the stoichiometric coefficient with a product of 2. So that means just multiplying with 2, I'll have 2I2 plus 2 into 2, 4 electrons, giving again 4I minus. Okay. Now the question is, how will my E0 value change? I have just multiplied the stoichiometry coefficient with 2. Will my E0 be multiplied with 2? The answer is no. Because just have written, it is an intensive property. It does not depend on the amount of substance. So it does not matter whether I take 1 mole of iodine or 2 moles of iodine. My E0 value will always be the same. And this shall actually be equal to E0 for this particular reaction will also be 0.54 volt. So E0 is intensive. It will not depend on the amount of substance. No matter how much the stoichiometry change, your E0 value will not change. Then what will change? When this reaction is being multiplied with 2, something should change, right? So the quantity that changes is actually delta G. E0 of cell will not change. Instead, what will change is delta G. Delta G value will change. Okay. So the numericals regarding these type are actually a bit confusing but very interesting to do. So we can move on to that after we study this particular topic. So the next topic that we're going to learn about is Latimer diagram. So what's a Latimer diagram? This is actually used for the metals which has variable oxidation state. So we represent this as a straight line or any way as we want, just by keeping the most oxidized species of the metal on the left, and then in each step we will write the reduced forms of the metal. So whichever oxidation state is actually feasible for that metal, all of them will be written, and the reduction potential values for every step will also be mentioned in the diagram. This is how you do a Latimer diagram. For example, let's write in case of manganese. So for manganese, let's see how the Latimer diagram will look like. So firstly, the most oxidized form, that will be MnO4 minus, in which manganese is actually staying in its +7 oxidation state. So in here, manganese is in +7 oxidation state. So from here, nextly we are reducing it, or the next possible oxidation state is Mn+6, in which it will be existing as MnO4 2 minus. So in here it will be Mn+6. The next species is MnO2. There it's MnO2 minus, plus. So in here Mn will be in +5 oxidation state. Next species is Mn3 plus. And then you will have Mn2 plus, and finally Mn in 0 oxidation state. Mn3 plus, Mn2 plus, and finally Mn 0 oxidation state. So just as I told, we are supposed to write the reduction potential values for all of this in each step. So for this step, that is from +7 to +6, the value is 0.56 volt. From +6 to +5, it is 2.26 volt. +5 to +3, 0.95 volt. Why have we skipped +4? The reason is +4 oxidation state is not that stable for manganese. Okay, the next is 1.51 volt for +3 to +2, and finally for +2 to +1 it is -1.18 volt. So in the Latimer diagram you see the variable oxidation states of metal from the most oxidized on the left to the least oxidized on the right, and the reduction potential is given for every particular step. So this is actually a very useful diagram. You will get to know the reduction potential values for every step. And another importance for this diagram is one can actually predict disproportionation. How can you predict disproportionation? What does it mean by disproportionation? It means one species can be oxidized as well as reduced in a particular reaction. So when can manganese or any metal in general be disproportionated? If you check their Latimer diagram, and if they have the reduction potential on right side greater than the reduction potential on left side, in all those scenarios that particular species can disproportionate, which means if the reduction potential on right is greater than the reduction potential on left, in these cases that particular species will disproportionate. So in here, let's see which of the manganese species can disproportionate. Firstly, Mn7 plus, it cannot go into further oxidation states, so this cannot be considered. Next, Mn plus 6, reduction potential on right is 2.26, on left is 0.56. Obviously, right is greater than left, so Mn plus 6 can undergo disproportionation. Nextly, plus 5. On right we have 0.95, on left it is 2.26. So right is less than left, so disproportionation not possible for Mn plus. Thirdly, Mn3 plus. On right we have 1.51 and on left we have 0.95. So right greater than left, therefore disproportion is possible for Mn3 plus. Next species is 2 plus. On right it's a negative value, on left it's a positive value. So obviously right is less than left and it is not possible. Mn0 cannot further reduce into Mn negative oxidation states, so that need not be considered. So which are the species which can undergo disproportionation in case of manganese? They are 1 Mn plus 6 and secondly Mn plus 3. Both of these can undergo disproportionation reaction. Now if I look into these diagrams, I actually know what is the potential when I move from Mn plus 7 to Mn plus 6 and from 6 to 5. But what if I want to find the electrode potential when I move from plus 7 to plus 5? In this case, how will I find the E value or E0 cell? Because I cannot add or subtract E0 cell. It is being an intensive property. It's not possible to add them or subtract them. So how will I find the change when I skip plus 3 oxidation state and move from plus 7 to plus 5 directly? So for this, there is only one way we can proceed with. That is, just because we told E cell will not change, only delta G will change, which means I'm going to proceed through the delta G values of these reactions. So if I want to find E cell for Mn plus 7 to plus 5, I have to find the delta G value for 7 to 6 and then 6 to 5. From this I have to calculate delta G value for 7 to 5 and then come back to the E value for 7 to 5. It's not that lengthy as it appears to be. Let's do a problem and see. Let's consider the case of oxygen. Okay, so we have O2, which is in zero oxidation state, and we are going to H2O2, in which each oxygen atom is in -1 oxidation state. And then to H2O, where the oxygen atom is in -2 oxidation state. So from 0, we are going to -1, then to -2. So I know from 0 to -1, the potential is 0.68 volt. From -1 to -2, it is 1.78 volt. I need to find how much will it be from 0 directly to -2. As I told, I have to proceed via delta G and not directly. So if I name them as, this one is E1, this is E2, and this is E3. So one thing I'm sure about is E3 is not necessarily equal to E1 plus E2. This is one important thing that I have to understand regarding the cell potential values. What we have discussed now also, we cannot simply add E values of cells. So instead, let's find the delta G value. What is the relationship between delta G and E? Delta G is equal to minus NF E cell. So for E1, I need to find delta G1. So delta G1 is equal to minus NFE1. That will be equal to, where N represents the number of electrons. So how many electrons? From 0 to minus 1, number of electrons involved is only 1. So this is going to be minus 1 into Faraday. I'll just represent it as F itself, because you will see why. Because in the end F will just cut off. So you need to apply the value there. Into E1. What is E1? 0.68 volt. So delta G1 is actually minus 0.68 into F. What about delta G2? That will be minus NFE2. So that is, from minus 1 to minus 2, how many electrons would be involved? Again, only one electron. So minus 1 into F into, what is E2? 1.78 volt. So overall the delta G2 will be equal to minus 1.78 into F volts. Now, as I told, delta G is extensive, which can be added. So I will have delta G3 will be equal to delta G1 plus delta G2. That will be minus 0.68 into Faraday plus minus 1.78 into Faraday. When you sum them up, you will get a value of minus 2.46 into Faraday. This is the delta G value for the third step, or directly from O2 to H2O. The delta G value is minus 2.46. But what I need is E0 value. So again, delta G3 is equal to minus NFE3. Since I want E3, I'll take it to the other side. So E3 will be equal to minus delta G3 divided by NF. And that will be, what is delta G3? Minus 2.46 into Faraday divided by, what is N value, or the number of electrons involved? From 0 to directly to minus 2. Therefore, there will be 2 electrons involved. So N value is 2 into F. I'll write as it is. Now you can understand why I did not substitute for F, because you can simply cut off the F. And we have minus 2.46 divided by 2. Answer will be minus 1.23 volt. So this is the answer, or this is cell potential for directly converting from O2 to H2O. So finally we have got that E3 value is equal to what? Minus 1.23. Minus 1.23 volt. And it's obvious that if you simply add 1.78 and 0.63, you're not going to get this value, right? There's one mistake here, because our equation already had a minus sign, and this is also a minus. You're supposed to put two negative signs here. This is minus 2.46 and a minus sign, so both of these will be cut and the value will be a positive value. So here we don't have a minus. Also here also we don't have a minus. Now also if you check, when you add 1.78 and 0.68, you will not get 1.23. Therefore, E1 plus E2 will not give E3, but delta G1 plus delta G2 will give delta G3, and from that we can find E3. This is how you should always do. Okay.